In electronics, a digital-to-analog converter is a system that converts a digital signal into an analog signal. There are several DAC architectures. The suitability of a DAC for a particular application is determined by figures of merit including resolution, maximum sampling frequency, and others. In this video, we see an example of a particular kind of DAC, the segmented DAC, which allows us to save room cutting the number of resistors needed. Our example is taken from the book Designing Analog Chip by Hans Camenzind, the designer of the 555 iconic circuit, about which I leave a link in the description. DAC converts an abstract finite precision number, usually a fixed point binary number, into a physical quantity, a voltage in our example. Here you see a very simple example of DAC. A string of identical resistors divides a reference voltage into 8 equal parts. Of 8 MOS transistors, only one is on at a time, connecting the selected tap to the output. Of course, with this circuit we can convert only 3-bit signal and we create analog signal of only one polarity. Let's see how it works more in detail. You see there are 8 resistors creating a voltage divider for the Vref voltage. Let's say our Vref is 8 volts. In this way, the code 000 switches on the first transistor and the 0 voltage passes through to the output. With the code 100, we switch the 5th transistor on and 4 volts pass to the output. With the code 111, we switch the 8th transistor on and 7 volts pass to the output. Being 8 resistors but 9 nodes, the Vref value cannot pass to the output, so the 8 combinations are converted in 8 analog values. Note that the analog values are only positive. To include the negative going values, we need to double the number of resistors and add an identical negative reference voltage. To represent bipolar values, some special codes are used. In the sign plus magnitude code, a bit is added which represents just the polarity. This is not the most efficient way, and it is somewhat awkward. There are 2 values for 0, 0, 0, 0, 0, and 1, 0, 0, 0. The offset binary code simply starts at the most negative number and counts up. Note that there is only one value for 0, but the full reference voltage is still not present. In the second complements code, positive numbers are the same as in binary code, with the additional sign bit. Negative numbers are the inverse or complement of the positive ones, with a 1 added and the sign bit changed. So for a signed 3-bit divider DAC, we need 16 resistors, and for a 8-bit signed divider DAC, we need 512 resistor segments. Definitely, you need 2 room. As the number of bits increases, the number of resistors explodes. Here there is a solution. A 6-bit DAC composed only by 12 resistors instead of 64. It is called segmented DAC. It is composed by 3 segments of 2 bits. On the left, the most significant bits, and on the right, the least significant bits. Of course, if you want the negative values, you need to double these numbers. A 6-bit number has 64 different combinations, so we can divide our reference voltage by 64, getting our minimum voltage range, or our maximum resolution. For example, if Vref is 8 volt, the minimum voltage sample is 0.125 volts, so the output voltage will have this maximum resolution. The output voltage values are multiple of 0.125 volts between 0 and 8 volts. Other values are not possible. So let's see how it works when Vref is 8 volts. Let's start from the most significant bits on the left. I have 4 identical resistors from R1 to R4, so Vref is divided into 4 equal parts by this voltage divider. Here we have a 2 to 4 decoder, so with 2 bits we select one and only one line at a time. For example, the combination 00 puts on the first line and we select the first resistor. So the below buffer shows 0 volt as output and the buffer above shows 2 volts. Now, in the second segment, we have 2 volt divided by 4 equal resistors from R5 to R8, reaching a resolution of 0.5 volts. For example, if the input bits are 1, 0, we select the third line, which selects the third resistor of the second segment. So the output of the below buffer is 1 volt and the output of the above buffer is 1.5 volt. So now we have 0.5 volts divided by 4 equal resistors, R9 to R12. So we get 0.125 volt as maximum resolution. If the least significant bits are 0, 1, we put the second line on and we select the node between the first and the second resistor of the third segment. So the output voltage is 1.125 volts. Note that we cannot put on the output the voltage on the top of R9, so our maximum output voltage is 7.875 volts instead of 8 volts. This is because, again, in 12 resistors we get 13 nodes and we want the value 0. Let's see another example. Let's say we have this input value, 100,110. We select the third resistor in the first segment, the second resistor in the second segment, and the third node in the third segment. So we are in this situation here. If Vref is 8 volt, the first segment selects the voltages between 4 volts and 6 volts. In the second segment we select the second resistor, so the voltages between 4.5 volts and 5 volts. The third segment selects the third node, so 4.75 volts, which is also the output value. From this schematic you can also understand the need of the buffers. They have to put forward the voltage in input decoupling the segments, so that the second segment doesn't load the first and the third doesn't load the second. If we imagine to have a direct connection erasing the buffer, in this node we wouldn't have 6 volts because we would see the resistance of the second segment and Vref 8 volt wouldn't be divided in 4 equal parts. Moreover, it is crucial that a DAC is monotonic, i.e., as you step through the code from low to high, the output always increases. For this reason, the connection have to be done as shown. For example, the 1-1 combination has to connect the higher possible value of each segment. Please leave me a comment, let me know if you liked this video. Make sure you put a thumb up, click the notification bell and subscribe to my channel.